What are you doing?
Well, I'm trying to make some different sounds from these two different cans.
Are those cans the same? Hello?
Hey man, there's some silly wacky sounds happening right now. You gotta check it out.
Oh, okay.
Hi, I'm Landyn.
Hi, I'm Marco.
Hello, I'm Darius, and we are SAS.
Equipment used for acoustic research and analysis is often very expensive and complex. This is the problem that our sensor-activated acoustic signal acquisition, visualization, and recognition device, or SaaS, is attempting to solve. The proposal for this project, as given to us by our client, Dr. Huda of Industrial Automation at NATE, was to create something that accomplishes this by being an Internet of Things-like device that is portable, easy to use, and is able to effectively analyze recorded audio using machine learning tools. From this proposal, we are able to set up a few main goals for ourselves. The device must record audio, stream live audio data to a user interface, visualize audio data on that user interface, save audio to a database, analyze audio using neural networks, and allow for user-controlled recording. This is the SAS hardware. It's just made up of a few components. The main component is this microcomputer here. This is the Latte Panda V1. We chose this because it has a capability of running multiple different operating systems and has a built-in Arduino Uno coprocessor. The microphone here is just a Max 9814 breakout board connected to a 100 microfarad capacitor, which is all connected to Arduino pins here on the Latte Panda. The device in its current prototype uses 10 watt power connected to mains. It communicates with the other subsystems using Wi-Fi. Here's the SAS UI. Right now it shows the device is not connected and not recording. If you start the device, it'll show that it is now connecting and ready to record. Once you hit record, you can see it is now streaming audio, and you can see the waveform reacting to my voice. And you can also see here, this light here means that it is sending serial data to the UI. While the device is recording, you can see three different graphs on the UI. The first graph just shows the intensity to time of the audio coming in from the Arduino. The second graph is a spectrogram of the frequencies that it is detecting in real time. Each level of the y-axis represents a different frequency, x-axis represents time, and then the brightness of each pixel represents the intensity of that frequency. And the third graph is an overall cumulative frequency density graph, just showing the overall density of each frequency within the recording. So to demonstrate the frequency readings, if I were to play a 400 hertz tone, you can see some lines start to appear here. If I play a 600 hertz tone, you can see some lines appearing a bit higher, and you can also see it showing up on the cumulative graph as well. And you can also play the frequencies together, and you can see here, now multiple frequencies are starting to spike. Once you are done with the recording, you can just hit stop, and it will save the recording to the database.
So for this part of the demo, we'll be seeing how the database works. So we'll just be opening it, and then as you can see, we are able to gather all of the audio data that's from the database. If we click one, we'll just click test 31 here. If you wait a little bit, it'll load in our visualizations based off of the data that's on the database. And if you open up ML description, then we get the outputs of the machine learning program. Here we can see which sections are recognized by the ML program in green and which parts of the wavefront are not. However, if you click demo test 1, you also get the audio data. So the waveform form and the spectrogram. But when you click the ML description tab, because this audio data is fresh and hasn't been processed yet, instead of the outputs of the machine learning processing, it instead shows a process button. Right now, obviously, it's a little rudimentary, and because we only have one machine learning program, this kind of works for our purposes, but in the future, it would be nice to have different options here. But if we click this button, and then we wait a little bit, the machine learning program will actually process the data, which shows which sections are recognized and which sections aren't.
So I'll be going over how we are formatting the samples so it can be compiled into the machine learning model. So we are using neural network binary classification, which allows us to easily swap between datasets when needed. For the sake of this demo, we will be detecting middle sounds where I have recorded beforehand. We first have our long recorded sample put into the not labeled files. Running this Python program will trim these files and move them into other folders, and those folders will be used for the model. The terminal asks for some configurations, like are you putting these samples into a training or validation dataset? In this case, I'll just be putting these into training. The second configuration asks to split the data by removing any noise below 20 decibels. Now we are going through the sample, listening to about half of a second of the clip, and moving the sampled sound to the corresponding folder. There is also validation data where we can use it to test how accurate our model is with the given known labels. The model extracts features, but in the case of audio samples, I have decided to use a MEL spectrogram, which takes the Fourier transform of a waveform.
In terms of SAS hardware and data acquisition, the main parts that we were able to integrate effectively was the data communications. The first main part that this can be seen in is in the data streaming. Getting the Latte Panda to efficiently collect serial data from the Arduino and send it to the UI in real time was a bit of a task. But we were able to use multiprocessing and WebSockets to approach this problem and allow the client running on the Latte Panda to communicate with both the Arduino and the UI concurrently. Efficiency was important as the client was taking on several tasks at once during audio recording. While one process was recording data, the other was doing minor pre-processing and sending the data through WebSockets. It needed to be fast enough, of course, so that the UI was able to show real-time data without much delay between when the hardware was collecting the data and when the user was seeing the data. Another part that we got to work well was the data saving. After recordings are done, they are sent to the database, and from there they can be accessed by the machine learning or UI subsystems. This part was much easier to implement as it wasn't real time and thus didn't really depend on processing speed.
Yeah, so for what worked on the visualization end, the biggest thing is that the UI can actually interact with other components of the system. So, communication with the hardware, communication with the database, and communication with the machine learning module. And we feel like that builds a really good base for, adding more features to the system. Another part of this that worked really well is that the basic visualizations actually load in, so the real-time visualization of data being streamed in loads properly and shows an intuitive graph of what's being recorded. And for previously recorded data, the data can get picked up and processed and then visualized as well.
For the analyzing of data, we have made a generic machine learning model that can be easily expanded upon or even substituted with another. We also made a validation dataset to check how well the model works. Please note that there are biases for these kinds of things, but the data seems to be around 85% accurate. From the visualization, we can see some potential in adding more features and showing off more information from the analysis.
In terms of what didn't work for the hardware, we greatly overestimated the audio quality that could be provided with the hardware that we chose. Overall, the serial communication between the Python client and the Arduino was limited. Data was only being sent in 8-bit samples, and we were only able to get a max sample rate of about 1.5 kilohertz from our data collection. This greatly reduced the accuracy that could be possible with our analysis techniques, and also reduced the frequency range that the device would be able to pick up. Initially, we were hoping that we could cover the entire human hearing range, which is about 20 hertz to 20 kilohertz. Another side effect of using an Arduino for data collection is that we weren't able to implement two-way serial communication and trigger sensors. Though it would be possible, adding more sensors and giving it the ability to listen to serial for instructions would potentially further reduce the audio quality being sent to the Python client, because it would ultimately reduce the number of clock cycles that could be spent on that data collection and sending.
Yeah, so for the visualization end, some things that didn't work was that some interfacing functionality wasn't properly implemented, and some of that sort of stuff is actually like quite practical. So things like editing the database, so deleting records, changing the names of records, being able to manipulate the machine learning model. Additionally, we also have visualizations that are pretty basic and not very generalizable or customizable, because the purpose of the system is to be accessible. That's something that shows a proof of concept but didn't exactly work out as well as it should have.
As of right now, the machine learning model uses synthetic data just because the hardware's sampling rate to get audio is not sufficient enough. Once the hardware is capable of recording a higher sampling rate, you can bet that these models will be more accurate.
There are a lot of things, hardware-wise, that need to be done to get the device closer to its initial goals. Currently, the device is running off of 10-watt power from mains, but it would be ideal to have this change to a more portable source. Either our goals for how long we want it to run will need to change, or the hardware itself will need to change in order to allow a cost-effective solution to be found. Another change that would need to be made is with how it's connecting to the other systems. The device is currently connecting to other systems via Wi-Fi, which is fine for demonstration, but when it comes to having a standalone user-friendly device, it is very limiting. We would like to have the device changed over to a cellular-based connection in the future so that it isn't tethered to a nearby LAN network. As mentioned earlier, the quality of the audio that the device collects is way too low for the purposes of neural network analysis, and the frequency range is also very limited. Future iterations should focus on getting these problems reduced as much as possible. A new data collection method would need to be found, and heavier preprocessing will need to be researched to find ways to bring the audio quality and frequency range up to what is expected from a research-based device.
Some future work on the visualization end is to implement some of those practical features that we were talking about, and some of them are pretty complex and the user can do them. They just have to access the backend directly. So abstracting a lot of that away from the backend and into the UI so the user can do it directly. Additionally, just adding some more customizable audio visualizations and information that's missing. So things like sample rate and stuff, it's really practical, but we're missing that for now. In the future, it would also be nice to kind of make a platform for customizable audio visualizations.
Since all of the main core functionalities have been finished, it is now a good time to improve the machine learning model's accuracy by modifying the pre-processing. We're also looking into upgrading from a binary classification to a multi-classification. We are also going to load models from the database instead of from a local machines folders.
So in conclusion, just to reiterate the purpose, ultimately this was to create an accessible and low footprint acoustic signal analysis tool. In the end, we were able to implement a lot of the core functionalities that we were looking to accomplish. Just a basic audio acquisition, audio visualization, and processing. There were a lot of practical features that we were missing, but ultimately we hope that the base system provides an easily expandable foundation for future iterations to add these features that we're missing and add even more features to accomplish the goal. And we want to say a big thanks to Dr. Huda for being a supportive client, and additionally to anyone else that helped us develop this project.